Okay. Today, we're going to start chapter 3, Matrix and Matrix Algebra. This has 7 sections, including matrix operation and inverse matrix and elementary matrices and subspace and linear independence and solution set of a linear system and its relation to the matrix and the special matrices. And LU decomposition, I will offer my lecture, but you don't have to worry about this for your midterm examination. Okay, here. Okay, we will define the matrix product here, and this also become an excellent tool in dealing with the function composition of functions. We define addition and scalar multiplication of matrices and introduce algebraic properties of matrix operations. It will be used to describe and relate the relation between solution set and matrix. Okay. And by using the Gaussian elimination, we will show how to find the inverse matrix by using the Gaussian elimination that you have learned in chapter 2. Further, we investigate the concepts such as linearly independence and subspace, which is needed to understand the structure of a linear system. Okay, and I will introduce some special matrices that will help you. First, section 3.1, matrix operation. Here is a English lecture and Korean lecture that you can see. Also, there is a web content that you can use. But actually, I made the new one here, so this will be enough to go through. Okay, in this section, we will introduce matrix operations, which is a generalization of the operations on real numbers. First definition, equality of matrices. We say two matrices are equal when they have a same size and every entries are same for all I and j. Okay? If two matrices have the same size and each entry is for arbitrary I and j, and then we call these two matrices are same, or these two matrices are equal. Okay. For example, if these two matrices are if these two matrices are equal, then it means W should be -1, and X should be -3, and Y should be 0, and G should be 5. These are both 3 by 3 matrix. If these two matrices are equal, then each entries should be same for every I and J, for all I, J entries. Okay? Okay. Addition and scalar multiplication of a matrix. When we have a two m by n matrix A and B, and scalar k, then the sum of two matrices and scalar multiplication on A by K are defined in this way. Like the ijth entry of A plus B matrix is just addition of ijth entry of two matrices, and ijth entry of Ka is just the k times ij's entry of A. Okay, so when we have these three matrices, we can find the addition of these two matrices or scalar multiple of those. And you will see. Since the size of these two matrices are same, so we can add these. But we cannot add A and C, because these two matrices are not same. The this matrix addition is defined when we have a same size, two matrices of same size. Here, so also we can check that easily. So let's define these three matrices in this way. Then we can find the addition of these two matrices and scalar multiple of A by 2, or scalar multiple of C by -1. And this is what we have here. And also we can generate it, and we see these are all matches with the answer. If we have a different matrices, then we can also find the vector addition and scalar multiplications. Okay? Okay. And matrix product, I think this is the first new things for you. When we have a two matrix whose size is one is m by p, and the other is a matrix of size p by n. M by p and p by n matrix. If we have these two matrices, the product AB of A and B can be defined as following. Okay? When we have this P and P are same, the column of A and the row of the number of column of A and the number of row of B are same, then this product can be defined by this way. The product of these two matrices will be the m by n matrix. M by n matrix. This P and P are cancelled each other. Okay, and ij's entry of this matrix is defined in this way. What this means is actually this. When we have these two matrices, the product is defined in this way. ij's entry of this matrix is product of inner product of this and this. Actually, ith row of A times j's column of B. So ai1 times b1j plus ai2 times b2j plus aip times bpj. This is what we define like this. This can be written in this way. Cij is ith row of A times j's column of B, like ith times j's column of B, like this. So you can multiply this and this to get this, which is the ij's component entry of the product matrix AB. We call this is King Sejong's rule, like 기억, okay? Like, So you shouldn't forget how you multiply two matrices. Okay? And suppose we have these two matrices, then AB, product AB can be defined in this way. So like this goes here. First row and second column goes here. Second row and first column goes here. Second row for second column comes to here. Okay? See, actually, when you have a two matrix like this, then the product of this matrix like this, which like what you had before. Using matrix product, one can express a linear system easily. Let us consider the following linear system like this. This can be written in a matrix form like this. AX is equal to B. Then, the unknown vectors and constant vectors respectively. Then we can express the linear system like this. AX is equal to B. It can be written in this way. And this can be written in this way. Do you understand that? You can, these xi's are all same. So you can just factor this x1, and these x2's are all same here, like this, and xn's are all same here. You can factor it out like this. Then this says, first, if you compare the first component, that is this. If you see the second component of this vector, this is the second equation. The last component of this vector, bmn, is 이거 고쳐야 된다. 이거 표시 좀 해주세요. b1, b2, bm. n이 없어져야 된다. Okay? Yeah, this b vector is this. Anyway, this bm is the last component of this equation, which is the last equation. So this can be written in this way. So this can be written in this way because x1 times first column of the matrix A and x2 times the second column of the matrix, and the last is xn times the nth column of the matrix A. Okay? This is same as AX is equal to B. So these are all same. So when you have this, you can use any of these for your own purpose. This is a property for the matrices, matrix algebra. Yeah, it is the matrix addition is commutative and associative, and it's also associative with the matrix product, and distributed row hold. And for if you multiply a scalar A and B, then it can be split in this way, like this, and this, and these are also distributive law with the vector addition and scalar multiplication together. Okay, these are the rules that you're already familiar with. Okay, this is easy to show. So, yeah, some of you try to prove one of these. For example, Mr. Kim Hyunjin, yeah, you may try to show one of these, like this. You may show this, okay? Show this and share it in Q&A. If you have any question, come to me, so I will help you to understand how you prove it. What you have to do is just when these two matrices are equal, all you have to show is ij's entry of this matrix is same as ij's entry of this matrix. Isn't it? That's all you have to show, because the size of those two matrices are same. Okay? When you have equalities like this, all you have to show is ij's entry of the matrix in the left-hand side is same as ij's entry of the matrix in the right-hand side. That's all you have to show. Okay, we can check these rules. When we have matrix A, B, and C, we can see AB times C is this, and A times BC is this. As you see, they are same, so we can easily. We can also check this with randomly generate the matrix A, B, and C and find this and compare those. So we can easily check that hold after we prove it. The property of operation of matrix are similar to those of operation of real numbers, which are well known. Yeah. So this is just generalization of the rules that you already have learned many times for real numbers. This is generalization. But you have to know we do not have AB is equal to BA in general. In scalar, in the real number, the product of two numbers are commutative. The matrix multiplication is not commutative. As you see here, suppose we have A and B, A, B, C, D, and like this, then it is DE is this, but ED is this. They are not same. So matrix is product is a generalization of the real number multiplication, but it has more than that. So you should know this. Okay, I made the GeoGebra manipulation for you to look, and So you can actually practice the interactive applet that you can see how this matrix product works. You can here setup에서 링크 열기. Actually, you can copy this somehow. Okay, like this. And you will see how this, when you have the matrix like this, if you multiply 2 here, then it will change. It changes. This shows how this, when you multiply the vector here, then the image should be different like this. So, but this is just simple things that you can just take a look. next definition is zero matrix. Yeah. The zero matrix consists of entries of zeros and denoted by zero, like m by n zero matrix. This is a 2 by 2 zero matrix, and this is a 2 by 4 zero matrix. And this is a 1 by 1 zero matrix. Okay. That's a generalization of real numbers to matrices. Theorem 3.12. Suppose we have a matrix A and zero matrix A of a proper size, then the following hold. Yeah, if you multiply zero matrix, it doesn't change anything. If you subtract a same matrix from the given one, then it is going to be a zero matrix. And if you multiply a zero matrix to any matrix, then it's going to be a zero matrix. Okay. Although AB is equal to 0, it is possible to have A and B are both not zero matrix. Okay, like this. A, B, C, D is given like this. The product of AD is a 0, but A is not a zero matrix and D is not a zero matrix. But product of these two matrices is 0. All. Okay? So this, we cannot say, even though AB is equal to 0, implies A is equal to 0 and B is equal to 0. It's not true in matrix product. And identity matrix of size n by n is defined as like this. It's an identity matrix whose diagonal entries are all ones, and one student asked it. Scalar matrix is a matrix has the same component, same case on the main diagonals and all others are 0. That's the scalar matrix is a scalar multiple of the identity matrix. But anyway, the identity matrix is defined in this way. This is the right definition. A is an m by n matrix. The important thing is, if for the m by n matrix A, if we multiply identity matrix of size m, then it's going to be the matrix A itself. If we multiply the identity matrix of size n on the right hand side, then it is going to be same matrix A. But since this matrix, the size of this matrix A is m by n, so if you want to multiply a matrix on the left, then it should be size some times n, and if you want to multiply the matrix A from the right hand side, then the column of the matrix should have n columns. So identity matrix has this property. Here, A is a matrix like this. When you have a matrix like this, then you multiply the identity. Yeah, we just checked those conditions here. Here. When you multiply identity matrix on the of proper size on the left, you have the same matrix. If you multiply the identity matrix on the right hand side of the proper size identity matrix, then it is going to be the same matrix. So if you define a matrix A and identity matrix of size 2, 3, and 0 matrix, then you will see the right when you multiply the identity matrix from the left and right are all same. If you multiply 0 matrix, then it's going to be a 0 matrix, always. Next, power of a matrix. The case power of a matrix is defined in this way. When you multiply the same matrix k times, then it can be written in this, and the zeroth power of a matrix is going to be identity, like the real number. Yeah. The 5 to the 0 power was 1, like this. So the zeroth power of each of the diagonal entries are going to be 1, so it's going to be a 0 matrix, identity matrix, something like that. It's a kind of generalization of those concepts. And if we have a square matrix A and non-negative integer R and S, then the power has satisfied this relationship, like what you already know. Okay, and you can check here. You can check this product. Like when you have a 2 by 2 matrix, then A square and A cube and A zeros powers, and A 6 power. This can be computed in this way, like you see. A square, A cube, A 0 power, and A 6 power, like this. This A cube of A square is same as A to the 6th power. So if you do the difference in 4 times 6, this should be same, isn't it true? But if you multiply, if this is not that like this, then it should be false. This is how those relations work. Okay, anyway, here the important thing is for the real number you have this equation. Square of A plus B is this, but in the matrix, this is what you have, not this. In general, A plus B square is A square plus AB plus BA plus B square. That's it. It's only, you can write it in this way only when AB is equal to BA. When AB's are commuted, then you can write it. If this condition is not given, you should be stopped here. You should stop here, okay? Transpose matrix, A transpose. Transpose of the matrix of A size n by n, then A transpose is a matrix of size n by n instead of m by n. The size of A transpose is n by n, and ij's entry, arbitrary ij's entry of this matrix is AJI. Just switch. Okay? If you switch the ij's entries in A transpose, like this. If you have A matrix here, then A transpose is a 3 by 2 matrix, and 3 goes here, minus 2 goes here, like this. And C transpose is a 2 by 3 matrix, and 4 goes here, 2 goes here, and 1 goes here, like this. Okay? Yeah, you can find the transpose with this comment. A transpose. D transpose, like this. Okay. And this is another property. And let AB be matrices of a proper size and K is a scalar, then the transpose of A transpose is A itself. And transpose of A plus B is A transpose plus B transpose. But this three part should be this. Transpose of AB is B transpose times A transpose. That is very important. And scalar case, K A transpose is K times A transpose. I think one of you can show this. Mr. Iseung-jin? Yes, I think you can show this. What do you have to do for this? We want to show two matrices are equal. So what do you have to do? Just compare the arbitrary ij's entry in the left-hand side is same as ij's entry of the matrix on the right-hand side. That's all you have to do. So just find ij's entry of AB transpose and find the ij's entry of B transpose times A transpose and show they are same. Then it's done. Okay? then AB is this, AB transpose is this, and B transpose times A transpose is this. As you see, they are same, like this. But this is not same as A transpose times B transpose. They are not same. They are not commutative. This is not same as A transpose times B transpose in general. You will see easily. So this is a kind of very different fact that from the algebra in real numbers. Okay? Trace, a new definition. Trace of the matrix A is just the summation of all diagonal entries. Just add the main diagonal entries. And that's called the trace. There are many reasons that we are learning the transpose and the trace of a given matrix. It has many applications. So you should know that. This is a property of the matrix, the trace. Trace of A transpose is same as trace of A because main diagonal entries of A is are same as the main diagonal entries of A transpose. So addition of all those same numbers should be same. When you have transpose, main diagonal entry doesn't change. Okay? It's a square matrix. And trace of CA is equal to C times trace of A. And trace of A plus B is trace of A plus B. And trace of A minus B is trace of B minus A minus trace of B. And trace of AB is equal to trace of B. The others are all easy. These are just it's easy, very trivial things. But for this, you have to show trace of BA, AB is same as trace of BA. This is the way to prove it. Just find the left-hand side. Trace of AB is the summation of these. This is the each of these are main diagonal entries of a matrix AB, and add all those together. And this is the main diagonal entry of BA, isn't it? And add all those. Then you will see they are same with this. Okay? So trace of AB, the scalar value is same as trace of BA. This is the way to prove it. Yeah. So yeah, this is the kind of technique that you should know also how to prove this. When A and B's are given, then trace of AB and trace of BA can be found like this. Here, trace of AB and trace of BA. They are, as you see, you will see they are same. If you change the matrices, still trace of AB and trace BA is the same. Yeah. When you change the size of this matrix, not by only 2 by 2, if you make a 5 by 5 matrix, still trace of AB should be same as trace of BA. Okay, that's the section 3.1. And next, 3.2, inverse matrix. Any questions before we continue? Inverse matrix, yeah, there are references for you here. In this section, we introduce an inverse matrix of a square matrix which plays like a multiplicative inverse of a real number. Okay? A square matrix A of order n is called invertible or non-singular if there exists a square matrix B such that AB is equal to identity and BA is equal to identity as well. If this matrix A is in this case, this matrix B is called the inverse matrix of A. If such a matrix B does not exist, then we call A is non-invertible or singular matrix. When A and B are given like this, then if we multiply, then AB is equal to identity and BA is equal to identity. Then B is an inverse matrix of A and A is an inverse matrix of B. When A is equal to given like this, then in this case, this has a 0 rows here, 0 rows. In this case, it does not have an inverse matrix because if we multiply any arbitrary matrix here, then always the third row of this matrix is 0 because of this. 0 times this, 0 times this, 0 times third columns are all zeros. So the third column of AB is always zeros. So there it is impossible to have identity matrix by multiplying any matrix for A. So this matrix is non-singular. Is singular. And this is non-invertible. This is non-invertible and it's a singular matrix. So if you define a matrix and ask whether this matrix A is invertible or not, then it will show it shows it is false. It is singular. It is non-invertible. If A is an invertible square matrix of order n, then an inverse of A is unique. When you show the uniqueness, suppose there exist 2 inverses of A, say B and C, then this satisfies, it should satisfy, and this should satisfy. But in this case, B is same as B times identity matrix, and B times AC because it's identity matrix. You can commute, we can use associative rule here. Then BA is an identity matrix, so identity matrix times C is just C. So this shows B is equal to C. So if you have a 2 inverse, then they should be same. So there's only one inverse matrix of a given one. That's why we write this inverse. Since the inverse matrix of a given one is unique, we write it is A inverse like this instead of B or C. You have learned when you have a 2 by 2 matrix, A inverse can be found in this way. If you multiply these two, you see this is identity matrix like. Inverse matrix has many properties, many nice properties. Inverse, if A, B are invertible matrices, then A inverse is invertible, then A inverse of A inverse is itself, then A, B inverse is B inverse times A inverse, not A inverse times B inverse. This is also very good. Orders are switched. Then inverse of Ka is 1 of K times A inverse, and inverse of A nth power is the nth power of A inverse. So I think we have to know how to prove this. How you can show it? When you show a given the two matrices are the inverse matrix of the other, then all you have to do is just multiply. Just multiply these two. This matrix times this. Then you will see, then show it is an identity matrix. Then B inverse can be cancelled and A inverse are cancelled as identity. So AB times this is identity. Also B inverse A inverse times AB is identity. So you can see it is invertible each other, and B inverse of AB is B inverse times A inverse. Okay? Not A inverse times B inverse. That's what you should know. A is invertible, then A transpose has the following form. The inverse of A transpose is this. How you show it? Just multiply this times A transpose. That's identity. Okay. For the square matrix, if you show one side, then you don't have to worry about the other one. But if it's not a square matrix, then you have to check both left and right multiplication. But for the square matrix, you don't have to. If it's an invertible matrix, it's a square matrix, so you only have to show just one side. AB is equal to identity. Suppose A and B are given like this, then we can check AB inverse is same as B inverse A inverse. Yeah, we can check, we can find the inverse of AB, and we can find the inverse of B times the inverse of A. You see they are same. This AB inverse is this, and the B inverse times A inverse is this. They are same matrix like what you have. Third, elementary matrices. And here is the information that you can use. And in this section, we define an inverse of a square matrix. Okay. And we discuss how to find the inverse of square matrix by using elementary row operations and elementary matrices. In fact, it's a Gaussian elimination. Let n by n matrix is called an elementary matrix if it can be obtained by identity by performing a single elementary row operation ERO, then we call it is an elementary matrix. We have identity matrix, okay, and take one elementary row operation, then there are one change is made. We call that matrix is an elementary matrix. Only one single elementary operation, okay, not two or three. For identity matrix, you take one elementary operation, then it's changed. That's an elementary matrix. That's an example of elementary matrix. Permutation matrix is obtained by exchanging the rows of I. You have identity matrix, you change the rows many times. Any of those matrices are one of the permutation matrix. So how many permutation matrices that we can have for n by n matrix? We have n rows. We can change n times, n minus 1 times, n minus 2 times, etc. So it's n factorial. So we have n factorial permutation matrix of size n. Okay? We have many permutation matrices. Okay, list below the three types of elementary matrices. Type 1 to 3. First, interchange two rows from the identity matrix. This is one example of elementary matrix of type 1. Second, multiply a scalar on one row. This is another elementary operation. It's we call the second elementary operation. Add 2 times the first row to the second row. Add 2 times first row to the second row. So add 2 times. So if you do the identity matrix, multiply 2 on the first row and add it to the second row, then you have this matrix. This is a third type elementary matrix. Okay. So actually, basically, these are the all type of elementary operations that you have and you can use. Okay. So for a given matrix, we can find the elementary matrix, and from a given identity matrix, if we change the second row and third row, then you will have this matrix. The second row and third row has been changed. If you multiply -3 on the third row, then like this. It's changed like this. If we multiply 7 to the fourth row and add it to the first row, then we have this. You should be aware that when you change the second row and third row exchange, I changed row 1 and row 2, but it's row 2 and row 3 were the intended. Do you know what's the reason why I use the first row and second row here instead of second row and third row? Because we are counting. This is in this language, in computational language, the first entry starts from 0. 0, 1, 2, 3, 4. So when you choose the first one, then it's going to be number 3. When you say third, in other words, if you say 2, it means the third one, from 0, 1, 2, like that. So that's the way. If you practice this, then you will see. You will see the elementary. If you to multiply like this, then you will see here, low here, scale -3 is 2 to 2, then you have what? You have this, multiply scale 7 like this, then you will have this. This is multiply 6,547 on the fourth row and add it to the first row. This is what we did. Okay? And properties. So, like this. When you exchange the second row and third row, this is, you just multiply this matrix on the left. So you change the second row and third rows, isn't it? From the given one. So multiply 3 on the second row, that means you just multiply this elementary matrix on the left. When you do this type of third type elementary operation, what that means is you just multiply this elementary matrix on the left to have the same matrix. Do you see? This and this are same. So what you did on the elementary row operation is exactly same as you multiply the corresponding elementary matrix on the left. Got it? Okay? So elementary row operation can be done by just multiplying corresponding elementary matrix. Okay? Inverse matrix, the inverse of the elementary matrix is elementary. Like you see, the inverse of this, when you multiply the same thing together, then you got the identity matrix. Isn't it? So inverse of this matrix is itself. Inverse of this matrix is inverse of this. When it's have a k, 1 over k, because we multiply these two matrices, it's going to be identity matrix. So inverse of this is this. When you have this matrix, and you multiply is minus c instead of c on the same position, then you will have identity matrix. So inverse of this matrix is itself. So and also the important thing is inverse of elementary matrix are all another elementary matrix. When you multiply k and you have multiply 1 over k, when you add, when you subtract, same. Okay? When you rotate it, then rotate it once again, then it's inverse. So inverse of elementary matrix, finding inverse of elementary matrix is very easy. Finding the inverse of an invertible matrix. When you have this is a way to find the inverse matrix. For any matrix, any n by n matrix A, the following are equivalent. A is invertible, then A is low equivalent to identity. Okay, this is what, yeah. And A can be expressed as a product of elementary matrices. Because when it's invertible, if you take elementary operations, finite time, then it will end with the identity matrix. So, AX is equal to 0 has only the trivial solution. That's the unique solution. Because A inverse does exist, multiply A inverse on both sides, then X should be A inverse times the 0 vector, which is the 0 vector. Okay? So X should be 0. They are all equivalent. This is the way. So with this in mind, when we have a matrix A, then take the Gaussian elimination, same as multiply elementary row matrix on the left. Then at the end is going to be identity matrix. Then what is the inverse matrix of A? This times this is inverse identity matrix. So this product of elementary matrix is the inverse of A, isn't it? Product of these elementary matrices is inverse of A. This is the whole idea. So when you do find the inverse, just to form a n by 2 n matrix. Matrix A and add the identity matrix on the right. Then you have a n by 2 n matrix. And do the Gaussian elimination. Just do the Gaussian elimination. Then at the end you will have identity matrix here. Then the next one is what? You just multiply the elementary matrices, corresponding elementary matrix, and it is exactly this, which is this, which is A inverse. So when you have an invertible matrix, just form a n by 2 n matrix like this and do the Gaussian elimination. Find the RREF of this matrix. Then what you have here is the identity matrix, the inverse matrix. Okay? So just this is algorithm. So when you have A matrix and then you make an augmented matrix A and the identity, then compute the RREF of this. So let's say the CD be a RREF of this. If C is identity matrix, then this D is inverse of A. If C is not identity, what that means is the matrix A is not invertible. Okay? Got it? Mm-hmm. So if this part is not identity, then this matrix has no inverse. That's it. That's the whole idea. So suppose we have a matrix A, then form a 3 by 6 matrix like this, do the Gaussian elimination, then what we have identity matrix. Then this is the inverse A. So this A inverse is this. Mm-hmm. So C is identity, so D is inverse matrix. When you have A, then to form it. In this case, you see, you have 0 rows here. So this is not identity matrix. It cannot be an identity matrix. We cannot go further to form an identity matrix. So it cannot be an identity matrix. Right? So in that case, you don't have the inverse of matrix A. So A inverse does not exist because C is not identity. Find the inverse of this matrix, then form an identity matrix, then form a matrix A and identity matrix, and make an augmented matrix, then find the echelon form. Then you have this. Then this is identity, so this part is the inverse of A. Can you do that? It is so easy to do so. Then next, subspace and linear independence. Okay, we will continue the last part of this. Any question on section 3.1, 2, and 3? Can you find the inverse matrix of a given one? Yeah, when it has the inverse. So all you have to do is just find the RREF of the n by 2 n matrix. Any questions?